Early in the 20th century, a strange and powerful breed of locomotive emerged deep in America's forests, machines engineered not for smooth steel rails, but for rails that bent, twisted, and broke under their own weight. These locomotives were not designed for permanence. They were built for logging railroads, temporary rail lines pushed rapidly into wilderness, often with no long-term plan beyond extracting timber as quickly as possible. When the forest was cleared, the railroad moved on or even disappeared entirely. The rails were never expected to last. The locomotives were. Logging railroads represented one of the most extreme operating environments in American railroading. Track was often laid directly on soil, mud, or stacked logs. Ballast, if present at all, was minimal. Curves were carved around standing trees rather than through them. Grades rose and fell wherever the terrain demanded. In this environment, derailments were not exceptional events. They were routine operational hazards. And yet, American steam logging locomotives operated day after day, hauling massive log trains over infrastructure that barely resembled a conventional railroad. Standard steam locomotives were designed for stability above all else. On mainline railroads, long wheelbases, rigid frames, and large driving wheels delivered speed and efficiency. Track was carefully graded, ballasted, and aligned to support those designs. Logging railroads inverted every one of those assumptions. Rigid frames resisted uneven rail joints. Long locomotives struggled with sharp curvature. Side rods bound when wheels lifted or dropped on warped track. Suspension systems designed for smooth rails became liabilities when rails shifted independently under load. After heavy rain, entire sections of track could sink overnight. During freeze-thaw cycles, rails heaved unpredictably. Ties cracked or crushed into soft ground. Spikes loosened and worked upward. A conventional locomotive encountering these conditions would derail, stall, or destroy its own running gear. Logging companies did not need speed. They did not need elegance. They needed tractive effort, delivered slowly, continuously, and reliably, even when the track itself could not be trusted. Rather than attempting to strengthen thousands of miles of temporary rail, engineers approached the problem from a different direction. If the track was going to fail, the locomotive had to keep working anyway. This thinking produced the geared steam locomotive, a category defined not by speed, but by torque, flexibility, and adaptability. These locomotives were engineered to creep rather than sprint, to twist rather than resist, and to distribute power across as many contact points as possible. Instead of concentrating force through a few large driving wheels, geared locomotives transmitted torque to every axle. This design choice had a direct consequence. Stress was no longer relieved by wheel slip or early failure. It was transferred relentlessly into the rails, ties, and ground beneath them. The most famous and extreme of these designs was the Shay. The Shay locomotive departed radically from traditional steam locomotive architecture. Instead of horizontal cylinders driving side rods, the Shay used vertically mounted cylinders along the side of the boiler. These cylinders turned a longitudinal crankshaft, which transmitted power through bevel gears to each truck. Every wheel was powered. Because the drivetrain was geared, torque remained consistent regardless of wheel speed. This allowed the locomotive to maintain tractive effort at extremely low speeds, which is ideal for for climbing steep grades with heavy loads. More importantly, it allowed the locomotive to continue delivering power even when individual wheels encountered uneven rail height, soft ground, or partial loss of support. If one wheel climbed a warped rail, the others continued pushing. If the track dipped, the locomotive adjusted instead of unloading force. This made the Shay exceptionally capable on logging railroads and exceptionally punishing to them. Because the locomotive rarely slipped or stalled, it did not fail early. Where conventional locomotives might derail or lose traction, sparing the track, the Shay forced the track to absorb the stress instead. If any steam locomotive truly earned the description designed to break the track, it was the 150-ton Class C Shay, also known as Western Maryland No. 6 or Shay No. 6. This locomotive was not experimental. It was not speculative engineering. It was a production machine ordered by logging companies who fully understood its consequences. By the time the Shay No. 6 entered service, logging operations were pushing deeper into steeper, less stable terrain. Loads grew heavier. Grades became more severe. Track quality declined as railroads extended rapidly into untouched forest. To meet those demands, locomotive builders did not reduce weight, they increased it. At approximately 150 tons, the Shay No. 6 was enormous by logging railroad standards. Its mass served a specific purpose: adhesion. The heavier the locomotive, the greater the normal force pressing wheels into rails. On steep grades and poor track, this translated directly into usable tractive effort. Where lighter locomotives slipped, the Shay No. 6 held on. That weight, however, came at a cost, one that logging companies knowingly accepted. Under the load of a Shay No. 6, rails flexed visibly, wooden ties compressed into soil or mud, spikes loosened under repeated stress. On lightly built track, permanent deformation was unavoidable. But the locomotive did not stall. It continued applying torque, transferring stress into the weakest component of the system. The track failed first. What made the Shay No. 6 uniquely destructive to track was not merely its weight, it was how that weight was driven. Rod-driven locomotives concentrate force through a limited number of driving wheels. When resistance increases, wheels slip or rods bind, relieving stress through loss of traction. The Shay steam locomotive did not behave that way. Its geared drivetrain delivered torque evenly to every axle. Resistance at one wheel did not reduce power output. It redistributed it. Other wheels continued pushing, maintaining overall tractive effort. This meant the locomotive did something unusual in railroad engineering. It refused to fail early. Where other locomotives might derail or stall, preventing further damage, the Shay No. 6 continued forward, forcing rails, ties, and subgrade to absorb the punishment. The Shay No. 6 rode on fully articulated trucks, allowing each axle group to pivot independently. This articulation allowed the locomotive to negotiate extreme curvature and uneven rail joints without derailing. It followed the track, regardless of how distorted that track became. But this adaptability carried an unintended consequence. Because the locomotive could tolerate warped rails, it allowed track conditions to degrade further before failure became obvious. Rails drifted farther out of alignment, ties crushed deeper into the ground. The locomotive adapted. The railroad deteriorated. Track maintenance became reactive rather than preventive. Crews repaired damage after the locomotive passed, not before. From a modern perspective, operating a locomotive that damages its own railroad appears irrational. For logging companies, it was an economic calculation. Rails were cheap relative to timber. Track was temporary by design. Locomotives represented the long-term investment. If a 150-ton Class C Shay steam locomotive could haul larger loads, climb steeper grades, and operate where lighter locomotives failed, then broken rails were simply an operating expense. The locomotive was optimized for output, not preservation. It was engineered to overpower infrastructure that was never meant to last. The Shay No. 6 represents a rare moment in engineering where failure was anticipated, just not by the machine itself. Rails bent, ties split, ground shifted, and the locomotive kept on going. It did exactly what it was built to do, and that is what made it so strange.